When we first met power series, we looked at this particular example, the power series whose terms look like x to the n for n values going from 0 to infinity. We said, hey, that looks a lot like the familiar geometric series. We know exactly when it converges and what it converges to. With that knowledge, we were able to say that for all x values between -1 and 1, it so happens that this power series adds up to the value 1 over 1 minus x. Therefore, on that domain between -1 and 1, we say that the function f of x equals 1 over 1 minus x has this power series representation. What we are going to do in this video is 5 examples of functions that look very similar to this one, and we're going to come up with their power series representations. So what that typically involves is taking an expression quite like this one and kind of doing some adjustments to the function as it's given to us so that we can bring in this relationship that 1 over 1 minus x equals this power series from -1 to 1. So the goal is to first take the function, do the adjustments. That's usually the hardest part. So figure out how to make it look like an alteration of this known function. Then once we've done that, bring in the power series. So we'll do examples, we'll do 5 of them. Then as we wrap up each example, we will identify the radius and interval of convergence. For our first example, we would like to find a power series representation for the function which looks very similar to the function we were just discussing, except that the numerator is x. So our function here, f of x, is x divided by 1 minus x. The goal with this kind of exercise is to take this expression and essentially rearrange terms as needed so that you're looking at something that reminds you of 1 over 1 minus x. For this particular example, what we're going to do is take the x from the numerator and pull it in front. So we'll have x times 1 over 1 minus x. Now this 1 over 1 minus x is exactly what we would like to see because we have a power series representation for that. So let's bring in the power series representation for this expression. I'm going to leave this x in front for now so that it's x times the power series from n equals 0 to infinity, x to the n. So I'm replacing this function with its known power series representation. Typically, what we would like to do is kind of bring everything inside of the sigma notation, if you will, so bring everything in. So I'm going to take this x and bring it inside. Let me do this once with an extra step. So here's the extra step, n equals 0 to infinity. I'm going to say x times this series is equivalent to x times every individual term. Because if I expand this out, I would be distributing the x. So that's x times x to the n. This is the extra step, though. Typically, what I would do at this point is write that this is the series from n equals 0 to infinity of x to the n plus 1. Okay, so that is a power series representation for this function. If I start to expand it, it's going to be x plus x squared plus x cubed plus x to the fourth. It's just like this one, except every term has been multiplied by x. What is the interval of convergence for this power series? You can use the ratio test if you'd like. So when in doubt, you can try the ratio test. And what you'll get is the radius of convergence is 1. You could then test the endpoints. If you didn't recognize, if you kind of lost sight of the fact that this whole computation was based on a known geometric series representation. Alternatively, what I like to do is go back to when I brought in my series. Like, where's the first moment I see the geometric series happen? It's right here. This leading x out here is just a number multiplying the series. So this is in front of this series. This will converge when this one does. So the question is, for what values of x does this converge? This will inherit that convergence. So because I know that this converges for all x between -1 and 1, that's the same result for our final computation here. So since x to the n converges on the open interval from -1 to 1. It's a geometric series here. It's not including the endpoints. That's what we have here. Okay, so our power series representation for this function, x over 1 minus x, converges strictly between -1 and 1. If you wanted to characterize this in terms of a radius of convergence, the radius would be 1, giving us a radius of 1 around the center of 0. So that wraps up our first example. We have 4 more to do, and all of them are going to follow the same thought process. Based off of this function, let's do some rearrangement of terms. It's not necessarily going to be as straightforward as this example, but we will kind of work through perhaps some more challenging examples. So we'll do some rearrangement, bring in the geometric series representation, and then we will see what we can deduce about the interval of convergence. Okay, for our second example, we are looking at a similar function. It's just one level up. This is x over 1 plus x. So the difference between this example and the previous one is the previous one was x over 1 minus x. Here it's 1 plus x. We are going to need to do something with that plus in the denominator, if you will. So let's write down what we have, x over 1 plus x. Just like before, I'm going to take that numerator and pull it in front. Okay, that's as far as we needed to go with the previous activity. But here, this is not quite right, if you will, because the known power series that we're basing all of these examples off of is for the function 1 over 1 minus x, not 1 plus x. So what we're going to do is take plus and replace it with minus minus, if you will. So this is going to be x times 1 over 1 minus negative x. Okay, and now we're good. We have here the right form, 1 over 1 minus something, and that something turns into the base for a geometric series representation. So this expression right here is like the r when we say 1 over 1 minus r for a geometric series. This is the new version of r for this example. So what we're going to do is now bring in that power series representation. We have that leading x. Again, that's not going to affect much. Just leave it out front. Then we have the series going from n equals 0 to infinity. It was whatever this was to the n, so r to the n. In this case, the r is negative x. So we'll write negative x to the n. Okay, let me pause there for a second so that you can kind of work through this step we did here with the denominator. Okay, now we've brought in the power series representation for the starting kind of classic function that we're building off of. All that remains to do is clean this up a little bit so that it looks a little bit more natural. Just like in the previous example, I'm going to bring the x in. I'm also going to take negative x to the n and think of this as negative 1 times x. So take this and write this as negative 1 times x. Negative x to the n is negative 1 times x to the n, but that's the same thing as negative 1 to the n times x to the n. So that's a common rewrite that we will see. So that overall, this becomes, I'll put it back over here. Let me go ahead and try to do all of that. So we are going to add up from n equals 0 to infinity, negative 1 to the n, x to the n, but then I also need to bring this x inside. So it's going to be x to the n times x, which is x to the n plus 1. That is the final version of the power series representation that we will have for this function. So this function has this power series representation. What is the domain for this power series representation, or what x values calls this equality to be true? Again, if you're not sure, you can do the ratio test and check the endpoints. But what I'm going to do is identify that this is really the geometric series that I'm basing this whole computation on. So this is my geometric series, which means I need the base, what I called r here, I need that to have an absolute value of less than 1. So we need, sorry, I want to write it exactly as I have it. So let me erase this. Second. Okay. We want to have the absolute value of negative x, this base here, less than 1. Well, that's the same thing as the absolute value of x is less than 1. So we're actually back to the same interval of convergence that we've seen already. This has an interval of convergence of -1 to 1. Around its center of 0, so that means the radius of convergence is 1. Okay, so that wraps up this example. Let's go on to the next one. All right, for this third example, we have 1 over 1 minus the quantity 5x squared. There's actually no adjustment that we need to make here, but let me highlight exactly how we're going to pass from this function to its power series representation. We have 1 over 1 minus something. It happens to be 5x squared. But this is exactly the form that we want to see in order to use this conversion that relies on our knowledge of the geometric series. So this expression right here is the base. So it's what we think of as r. So 1 over 1 minus 5x squared, we can pass immediately to a power series. This is going to be the series adding up from n equals 0 to infinity, this base to the n. That is the first step. Now, just like before, let's just try to make it look a little better. We can do 5 to the n times x squared to the n. That's going to be x to the 2n. So this, in its final form, should be the series going from n equals 0 to infinity, 5 to the n, x to the 2n. So if we expand this out, we will only see even powers of the independent variable x. Okay, that's a power series representation. What is its interval of convergence? And again, it's going to rely on this base, knowing how geometric series converge. Here's the series that I would actually look at in order to work out what the interval of convergence is. We need this base to have an absolute value less than 1. So we can say that we want 5x squared to have an absolute value less than 1. Well, this is always a positive number, but I've written absolute values because that's the general principle. I can just write this as 5x squared less than 1, or in other words, x squared needs to be less than 1 over 5. So if x squared is less than 1 over 5, that means the absolute value of x is less than 1 over the square root of 5. So I took the square root of both sides. You have to keep in mind here that x could be between 0 and -1 over the square root of 5, and be squared to a number less than 1 over 5. So that tells us that the interval of convergence is -1 over the square root of 5 through 1 over the square root of 5. Again, it's a nice open interval. The radius is this 1 over the square root of 5. Okay, so that wraps up that example. For this fourth example, we will see some things that look like techniques we've already done before, but we'll have one new aspect to this computation. So we are looking at the function f of x equals x cubed divided by x plus 10. This feels like something that can be reworked into the form of our kind of classic prototype 1 over 1 minus x. The first step won't surprise you. Let's take that numerator x cubed and pull it out in front. So we'll have x cubed times 1 over x plus 10. Okay, so far so good. I'm going to do something here that feels a little redundant or silly, but I'm going to take x plus 10 and rewrite it as 10 plus x, just because what we're working towards is 1 over 1 minus x. So I just rather see x in the second position in this denominator. So let's have x cubed times 1 over 10 plus x. Why not? Okay. What's new about this example is that this number is not 1. Okay, it's 10. The prototype is 1 over 1 minus x, not 1 over 10 minus x. So what we're going to do is take this 10 and factor it in front. I'm actually going to put it with the x cubed so that this becomes x cubed divided by 10 times 1 over 1 plus x over 10. Now, if you look at this, if I multiply these back, the numerator will have x cubed, that's what we started with. The denominator will have 10 plus 10x over 10, or in other words, 10 plus x. And so we haven't actually changed anything, but now it looks better. The addition here we know how to handle. I'm going to replace that with minus a negative quantity. Let me go ahead and move down to the next line so that we can say this expression is x cubed divided by 10. That's just going to hang out in front times 1 over 1 minus negative x over 10. Okay. Now we see the right form where the base that we want for the geometric series form that we're about to put this in has this base r taking the expression negative x over 10. Okay. So we can convert this to a power series. This hangs out in front just for another minute. So let's write this as x cubed over 10 times the power series going from n equals 0 to infinity, negative x over 10 to the n. All right. Let me pause there so you can catch up if you would like to think through any of these steps that I did to get to this part. When you're ready, go ahead and see what you can do here. Bring this in, kind of take this to its final form. Then what we will like to do, just to wrap up this example, is to figure out what the interval of convergence is. So we just need to write this one more time in a nicer form and also figure out the interval, the radius of convergence. Okay, to take this one step further, let me write its final form right here. We are going to have a power series going from n equals 0 to infinity. The negative here is going to be a negative 1 to the n. So just like we saw in a previous example, whenever you have negative x, think of that as negative 1 times x, and then both of them are getting exponentiated. Both of them are being raised to the nth power. So if I collect my non-variable terms, my coefficients, I'm going to have negative 1 to the n. And then in the denominator, we have 10 to the n plus 1. Okay, so that takes care of the negative, the 10 to the n, the 10 here. For the variable, we're left with x to the n plus 3. Okay, so that is the power series representation for this function. To find the interval of convergence, again, what I recommend doing for this kind of construction where we're basing it off of a geometric series is to go back to this step here, where I took my base and I said, okay, given this form, here's the corresponding series. This expression here is going to give us the condition that we need on x. So in particular, we need this base, what I'm calling r, to have an absolute value less than 1. So for convergence, we need to say that the absolute value of negative x over 10 is less than 1. So that means that the absolute value of x is less than 10. That gives us an interval of convergence of negative 10 to 10. And of course, the radius is 10. All right, we have one more example. Here's our fifth and final example in this video. We would like to find a power series representation with interval of convergence for the function f of x equals 7x divided by 2 to the fifth minus x to the fifth. There's actually nothing new here. So everything that we're going to do to this function is something that we've already seen in the first 4 examples. So let me pause and see what you can make of this. So take it as far as you can, and then I will come back and finish the problem. Okay, just like we've seen several times, the first step is to take the 7x from the numerator and just pull it in front. So we have 7x, 1 divided by 2 to the fifth minus x to the fifth. Just like we discussed in the previous example, the 2 to the fifth isn't great in its current position because the prototype is 1 divided by 1 minus the base r. Okay. So I'd rather have a 1 here. That's what's going to prompt me to pull the 2 to the 5th out in front. So I can write this as 7x divided by 2 to the 5th times 1 divided by 1 minus x to the 5th divided by 2 to the 5th. Or if you like it better, that's 7x divided by 2 to the 5th times 1 over 1 minus x over 2 to the 5th, like that. Okay, now we're ready to go with the power series representation because we've got 1 divided by 1 minus something, where again, that something is what we can think of as the base for a geometric series looking power series representation. Okay, so let's go down here and say that our function can now be written as 7x divided by 2 to the 5th times the series index from n equals 0 to infinity, this to the n. So it's going to be x over 2 to the 5th to the n. We just have to clean this up a little bit. Before I clean it up, I just want to mention this is what's going to go into our interval of convergence computation. So it's like this moment is where I start looking for my radius of convergence. With that in mind, let's proceed onwards. So the 7 is just a 7. I will bring that in now and kind of collect terms inside of series notation. So we'll have a 7 times 2 to the 5n plus 5 in the denominator, 2 to the 5n plus 5, and then x to the 5n plus 1. I feel like you could write this as 7 divided by 2 to the 5n plus 5 times the quantity x to the 5n plus 1. I think that's everything. Looks right. That's our power series representation. For the interval of convergence, we want x over 2 to the 5th power to be less than 1. This is equivalent to the absolute value of x over 2 less than 1. That means that we want the absolute value of x to be less than 2, so that the interval of convergence here is from -2 to 2 with a radius of 2. Okay, so that wraps up this final example. All 5 examples had a similar theme. What we wanted to do was take a function which reminded us of 1 over 1 minus x and rearrange terms, do some rewriting so that we could bring in something that looked like 1 divided by 1 minus an expression that we then put into that power series representation that we already knew for that function 1 over 1 minus x.